Work function is the minimum energy required by an electron to escape from the metal surface. We know that there are free electrons inside the metal, but they cannot come out of the metal surface as they are pulled back by the positive ions inside the metal. Work function can be provided to an electron by three different methods. First one is thermionic emission. Sufficient thermal energy can be imparted to free electrons to enable them to come out of the metal. The second one is field emission. By applying a very strong electric field, electrons can be pulled out of a metal. The third method is photoelectric emission. When light of suitable frequency illuminates a metal surface, electrons are emitted by the metal surface. These electrons are called photoelectrons. This is the experimental setup to study photoelectric effect. We have an evacuated tube with a window through which ultraviolet light can be allowed to fall on the cathode C. Now photoelectrons are emitted and they are collected by the anode. Current due to photoelectrons flow through the circuit. Here we have a commutator to change the voltage of anode and cathode. A microammeter to measure current and voltmeter to measure voltage across anode and cathode. Effect of intensity of light and photoelectric emission. By keeping the frequency of incident radiation and the accelerating voltage fixed, the intensity of photoelectric current is varied. That is, the number of photons falling will increase. From figure we can see that photoelectric current increases with the intensity of incident radiation. Here we have plotted intensity along the x-axis and photoelectric current along the y-axis. We can see that photoelectric current is directly proportional to intensity of light. Effect of potential on photoelectric current. Here we have anode potential along the x-axis and photoelectric current along y-axis. Illuminate the plate C with light of fixed frequency and fixed intensity. We can see that for intensity I1, as the anode potential increases, photoelectric current increases at first, after which it remains constant. When the potential of A is increased, photoelectric current increases with increasing voltage. For a certain potential of A, all the emitted electrons are collected by the plate A. Further, the photoelectric current becomes maximum or saturated. This maximum value of photoelectric current is called saturation current. Now all the electrons are absorbed by the anode. Now apply a negative potential to A with respect to C. Electrons are repelled and only the most energetic electrons reach A. Photoelectric current decreases and becomes zero at negative potential V0. This V0 is called stopping potential or cutoff voltage. That is, for a particular frequency of incident radiation, the minimum negative potential given to plate A so that the photoelectric current becomes zero. This potential is called stopping potential. It is represented by minus V0. Now the plate A repels the most energetic electrons with maximum kinetic energy. That is, the electrons are having maximum kinetic energy. Now we can write K max is equal to E into V0. If we increase the intensity to I2 and I3, the saturation current increases but the stopping potential remains constant. Or stopping potential is independent of intensity. For all the three intensities, here we have the same stopping potential minus V0. Effect of frequency on incident radiation. The intensity of incident radiations are kept constant and frequencies are varied. We obtain different values of stopping potential. That is, for frequency nu1 we get minus V01. For a higher frequency V2, nu2 we get minus V02. And for nu3 we get minus V03. So the stopping potential increases towards the negative side. As the frequency increases, the stopping potential becomes more negative. Greater is the frequency of incident radiation, greater is the kinetic energy of photoelectrons. So great stopping potential is needed to stop them. The saturation current remains constant for all the frequencies. The variation of stopping potential with frequency. If we take metal A, we can see that stopping potential varies linearly with frequency for a given material. There is a certain cutoff frequency nu0 for which stopping potential becomes 0. For metal B, we can see that potential varies with frequency. We can summarize the experimental results. For a given photoelectric material and frequency of incident radiation, photoelectric current is directly proportional to frequency. For a material and frequency of incident radiation, saturation current is proportional to intensity of radiation, but stopping potential is independent of intensity. For a given photoelectric material, there is a minimum frequency of the incident radiation called threshold frequency, below which there is no photoelectric emission. When frequency is greater than threshold frequency, stopping potential and kinetic energy of the electrons emitted increases. And photoelectric emission is an instantaneous process, that is, time lag is less than -9 seconds.